So here we go, lesson 7, Newton's law of cooling. You guys know or should have heard of Sir Isaac Newton. He has made major contributions to math, science, theory, and this is just one of the many contributions that he has made, his law of cooling. So this is the formula. Don't let it freak you out. I mean, yes, it looks kind of crazy. What are all these weird looking things here, right? This is not on the reference sheet. However, I have never seen this on the Regents with them not giving you the formula within the question. So when you have it on a test or a quiz, it will be given to you in the question. And it does also give you these little explanations over here about what each thing represents, right? And I'm going to talk about that quickly. So T of T, which is the left side, it's the temperature after the object, after time has passed, right? If there's an initial temperature, this would be the temperature that it ends at, or, when you're trying to calculate something. T sub, and it looks like a little A. It's actually an alpha, the Greek alpha. It's the ambient temperature, the temperature of the surroundings, the room temperature. Okay. And it is so if you're, looking at the room temperature, we're going to assume that nobody has touched the heat or the air conditioner, that the temperatures would have been the same the entire time. T sub 0 is the initial temperature, so it's they're using something different, right? They kept using A before P for principal, but it's the same idea. It's the initial temperature of the object. K is new. It's the decay constant per time unit. So this is sort of new. This is sometimes given to you, but even if it's not, there is a way to figure it out. Okay? Exercise 1. A detective is called to the scene of a crime where a dead body has just been found. He arrives at the scene and measures the temperature of the dead body at 9:30 p.m. to be 72 degrees Fahrenheit. After investigating the scene, he declares that the person died 10 hours prior at approximately 11:30 a.m. A crime scene investigator arrives a little later and declares that the detective is wrong. She says that the person died approximately at 6 a.m., 15.5 hours prior to the measurement of the body temperature. She claims she can prove it by using Newton's law of cooling. Using the data collected at the scene, decide who is correct, the detective or the crime scene investigator. All right, so they have given you a lot of the information. Normally they won't do this, but since we're just learning it, a lot of it is given to you. So T sub A or T sub alpha is 68 degrees. That's the room temperature. Again, we are assuming that that is constant, that it's not, the heat hasn't been turned on or the air conditioner. T sub 0, the initial temperature of the body, 98.6 degrees. This is never actually really given to you in a problem. This is assumed to be common knowledge that the initial temperature of the body is 98.6. K is the decay constant. So it is the rate at which there is a decay. So this has been found for you. It's lucky when they give it to us. It makes life easier, okay? So they're saying 0.1335 or 13.35% per hour. and that was calculated by the investigator from the data collected. Now, we want to remember that the temperature of the body at 9:30 p.m. is 72 degrees. So that is our T of temperature when we start calculating things or after the time has passed. Okay, so here is my formula. I just moved it down so I have enough room to write. So we're going to plug in all the information that we have. So we do know that T of T is 72 degrees. That's the temperature after time has passed. T of alpha, sub alpha or A is the temperature of the room. So that's 68 degrees. The initial temperature of the body, we are going to put in 98.6 degrees minus the room temperature again. So yes, that's in there twice. I didn't mention this earlier because we were just talking about what everything stood for, but please notice that there is an E in this equation, the E that we know. There's so much going on in this equation that it's easy to lose that E, but if you lose it, it's going to mess everything up. And then negative 0.1335, and we don't know the T. We're going to figure out how long it took to go from 98.6 degrees to 72 degrees. Now, I know this formula looks really overwhelming. It's huge. There's a lot going on. But it is just a formula, just like all the other formulas that we use, all right? I am solving for T. T is an exponent. I'm going to use a log at some point. I've said this like 8 million times in the past 2 weeks, right? So that means we need to get E, our base, alone. So I'm going to simplify. First and foremost, I am going to simplify what is in my parentheses there, so I have a single number, which is 30.6 e to the negative 0.1335 t. Let me just make that a little bit bigger there. All right. So I am now going to subtract 68 from both sides. That's going to give me 4. And now I'm going to divide both sides by 30.6 because that's in front of the E. I want to get rid of that. And I do get a crazy decimal. I'm just going to write down the crazy decimal. I mean, you could keep it as a fraction. It's up to you, but really, I mean, our exponent's a little crazy. So let's just be consistent with the crazies. Okay, in the same step, I'm going to, actually, I don't want to be confusing. Let me just switch my natural log to my answer to the right, because I know I'm going to need the natural log. So I'm just changing my order yet again. Okay, I have E. I'm going to use my natural log here. I must do it to both sides because it's easier to take the natural log of E, which is 1. Now I'm going to take my exponent and put it down in front, but I'm going to bring this all up to the top, or to the right side really, just so it's not all squished in there. So I have negative 0.1335 t. Natural log of E equals the natural log of that crazy decimal. Okay, natural log of E is 1. Divide both sides by the K, or the negative 0.1335, and that's going to cancel. So I'm going to put that whole right side of my equation in my calculator, and when you do that, you should get 15.2412. I might have rounded that a little bit. And we're going to do it to the nearest hour. So we're going to say about 15 hours this body has been dead. Okay. So the question is, who is correct? Was it the detective or was it the crime scene investigator? I'll give you a little hint. The crime scene investigator probably has more technical skills when it comes to this stuff, right? They're trained in that kind of thing. So we're saying about 15 hours, and the crime scene investigator is a she, and she said 15.5. So yeah, we rounded this, it was 15.2. So we rounded it to 15, but wouldn't you say that's a lot closer to 15.5 than 10, right? So we're going to say the crime scene investigator. I used to watch that show all the time, by the way. Okay, and there we go. All right, we have another detective called to another scene where a dead body had just been found. She arrives on the scene at 10:23 p.m. and begins her investigation. Immediately, the temperature of the body is taken and is found to be 80 degrees Fahrenheit. The detective checks the programmable thermostat and finds that the room has been kept at a constant 68 degrees. Assuming the victim's body temperature was normal, 98.6 degrees Fahrenheit, prior to the death, and that the temperature of the victim's body decreases continuously at a rate of 13.35% per hour, use Newton's law of cooling to determine the time when the victim died. A lot of the same numbers here, but that's okay because we're just practicing. So the first thing I'm going to do is correctly copy the equation onto my paper. Now what I'm going to do is I'm going to identify all the things that I need to put into the equation. I find that helpful to do, especially when we're just learning. So T of T is the temperature after time has elapsed. So the body temperature when they found it is 80 degrees Fahrenheit. T sub A is the room temperature. So that is 68 degrees. T sub 0, the initial temperature, body temperature, is 98.6. And K, that's the same number, but it needs to be a decimal, so 0.1335. You will notice that number pop up a lot. And we need to figure out how long it's been there, how much time has gone by. So again, T is unknown. I'm going to now plug all those things into my formula. Don't forget that E there. I am now going to follow the same steps that I did on the previous page. I'm going to simplify what's in my parentheses first, and that's going to be 30.6 again. Subtract 68 from both sides. So this number is going to be slightly different. It's going to be 12. Divide both sides by 30.6. Probably going to get another crazy decimal. Also, I'm going to save myself a step and write my E on the left side. And the decimal I got was 0.39215686627. If you wanted to leave that as a fraction, you can. I am going to insert a natural log on both sides, and in one big swoop, put that exponent down in front. I'm also okay with you getting rid of the natural log of e right before this step, but I'm not going to do it just for the sake of being consistent. Now that's gone. The natural log of e is 1. Divide both sides by that k. So when I put that whole crazy looking thing in my calculator, I get 7.0119 to the, when we're talking time, you don't want to go out more than 2 decimals anyway. So we're going to say about 7 hours, give or take a few minutes. All right. But the question is not asking how long did it take to cool. The question is asking at what time. So if it's 10:23 p.m. and we know the body's been dead for 7 hours, we're going to subtract 7 hours. Be careful with time. It's in groups of 10, right? And so that's going to give us around 3:23 p.m. And this is where they start eliminating suspects. We're rounding up people and asking what their alibi was at that time. All right, now for the sake of this being new and these equations being, these formulas being very overwhelming, I'm going to stop with the lesson and I'm not going to go any further. But I do want to talk about your homework. So I want for you to look at the first page of the homework. I actually think this homework is so, I don't know, it's not good. It needs to be redone. I want you to only do question number 1. However, I want you to listen to me carefully because I'm going to add to it a little bit, all right? You're going to read question number 1. I have no idea what that little question mark is on mine. I don't know if that's on yours, but you're going to do question number 1. You're going to answer the questions. They're pretty straightforward questions. It is Newton's law of cooling, all right? For the second part, you're probably going to need to do this on a separate sheet of paper because you're not going to fit this all in here. So I'm just going to call this like 1B. I want to know how long will it take for the soup, aren't you glad it's not a dead body, to cool, yeah, if I could spell cool, to 100 degrees Fahrenheit. All right. So they already put it in the equation for you and asked you what everything was, which makes it a little easier. But you are going to plug in the 100, find T. Okay, that's all you have to do, but I want it done well. And I will see you guys on Monday. Have a fabulous weekend.